Samuel, the stage is yours.
Thank you. Hello, I'm Samuel Iglesias, member of the graphics team at Igalia. In this talk, I'm going to explain how to improve Khronos CTS coverage using Mesa code coverage. First, a few words about myself. I have been contributing to Mesa and to Piglit for 6 years, and I have been contributing to the Khronos Conformance Test Suite for 3 years now. I'm also a board member of the XOR Foundation since 2019. What is Khronos CTS? It is an open source conformance test suite developed by the Khronos Group. It is mandatory for the drivers to pass the respective OpenGL or Vulkan tests in order to get the respective conformance. Furthermore, CTS is very useful for pure driver development. We can test implementations of new extensions, features, or even detect regressions. Unfortunately, there are cases where CTS is the only source of test for specific extensions or features, especially for the newer ones. Because of that, the test coverage is very important. There are several ways to come up with new tests. First, we have the traditional approach, which is doing the normal test development, like, for example, developing tests for new extensions. Then there is another way, which is when the driver developers realize that there are missing test coverage in CTS. For example, we collaborate with our colleagues at Igalia that develop the graphics drivers for the Raspberry Pi 4 in order to develop the CTS test that they found gaps in the coverage. There are other approaches, like, for example, fast testing, that, for example, could provide invalid, unexpected, or even random data as inputs to the different API functions, or to say their opcodes, among other things. One example of this work is the Google project called Graphics Fast. In this talk, I'm going to talk about another way to find new missing coverage for CTS. It is based on analyzing the Mesa code coverage after running the whole CTS suite on different drivers. Let's start first with the setup. For doing the Mesa code coverage, we use our own existing internal GitLab CI, which uses Docker internally. Our internal CI was used for Intel GPU driver development, so it made sense to reuse it to run the tests there to get the coverage data. Also, because the Intel drivers are very mature and have support for lots of extensions and features, it makes totally sense to use those machines. Similarly, we test AMD Mesa drivers, including both ACO and LLVM backends for the RADV driver, as they are very mature as well. In this talk, I'm going to focus on Vulkan drivers, and this was our first goal, as it is where CTS test development is under heavy work, and the test coverage is very important. Also, the procedure that I'm going to explain in these slides works the same for OpenGL drivers. First step is to create a Docker image with a Mesa build with code coverage support enabled. As we are using GCC toolchain, we use Github for doing that. In that Docker image, we also have the CTS build that we are interested on testing, like, for example, a specific development branch of CTS or a public release. Then, once we got these Docker images, we run them on different machines in order to get info from different drivers, as they may support different extensions or features. We also run on different generations of the same GPU family in order to get a better idea of what has been testing or not. Finally, we generate an HTML output with the coverage results using LCOV. Also, sometimes we push the data to a third-party service like CodeCov if we want to share it publicly. This is an image of our GitLab CI pipeline. We have 4 stages here. First one is the Docker image generation. The second one is the execution of it on different drivers, backends, generations, etc. The third step is the one that is gathering all the results, and the last step is to publish it to a third-party service, and so on. This is a screenshot on how LCOF looks like. As you can see, it is quite simple. We can dive into any folder of the source code and see the code coverage per line of specific files. We can also see stats of the overall coverage per folders and files if you browse into these folders. For example, this is a screenshot of part of the SPIR-V to near.c file. This file is the one processing SPIR-V instructions and translating them to near intermediate representation. On the left, it has some counters to indicate how many times a line was executed over the execution of CTS, in this case. The same information is provided by a third-party service like opcode. You can navigate through the source code folders and see the coverage per file and the stats of the overall code coverage per folder profile, like I just explained with LCOF. Although CodeCof provides the same information than LCOF, it is a bit confusing. Notice that on the left, the number there is not the number of times a line was executed. It shows how many code coverage runs has hit this line. In this case, it means one CTS run. If you want to know how many times a line was executed by this CTS run, you need to put the mouse on top of the number and it will show it to you. GCOF is a great tool, but it is not perfect. One issue we faced was related to fall-through switch cases. GCOF doesn't keep the counters of how many times a fall-through switch case is executed, or if it's not executed at all, or selected at all in the switch, which is problematic to detect SPIR-V opcodes that are not being tested. For fixing that, we wrote a script that adds a couple of dummy lines between the fall-through switch cases to see if, for example, the SPIR-V opcode is actually executed or not. Thanks to that, we can easily detect missing coverage here. Once we got the Mesa code coverage results, it is time to analyze them. We currently do it by hand. In this talk, I will focus only on Vulkan drivers, but for OpenGL drivers, the process will be very similar. For Vulkan API entry points, we check those that are provided by the drivers that we are analyzing. We check if all the arguments are used, for example, or there is a missing case that can be easily spotted by checking the coverage of the source code. Before talking about how to analyze SPIR-V opcodes, let's start with a diagram of the Mesa shader compiler architecture. We typically start with a GLSL shader that can be compiled directly by Mesa, like, for example, in the case of OpenGL, or we can process an SPIR-V shader. If we focus on Vulkan, the SPIR-V shader will be translated into near intermediate representation. And from there, it's going to be used by the driver's backend in order to generate the assembly code that is going to be executed on the GPU, either directly or using LLVM as an intermediate step. So for checking the coverage of SPIR-V codes, we look at different places. The main one is source compiler SPIR-V folder, which is where all the SPIR-V opcodes are processed and translated into their equivalent on near. However, we found that sometimes the SPIR-V opcodes can be used with different data types, and its processing here is generic enough that we don't know if any of these different data types is missing in the coverage. For that reason, we also check the driver's backend compiler, because in some cases, these generic cases are managed separately in the drivers, and we can find easily if there is any missing coverage in a given SPIR-V opcode. As one driver can split some SPIR-V opcodes, but not others, and the other way around for other driver, this is the reason that we are running the test on different drivers. As I said before, currently we are only focused on RADV and Anvil because they are very mature and very feature complete. One example of this work is this one. Thanks to ECHO, we found that some relational operators were not tested on 64-bit data types. Thanks to this analysis, it was easy to add them in CTS, actually. The conclusions of this work are the following ones. We use an different open source tools as GitLab and Docker for this work. Thanks to running this code coverage analysis, we found that nowadays CTS coverage is pretty good already. One thing to improve is that we are analyzing the Mesa code coverage by hand right now. We have some ideas to automatize it that we are planning to do it in the future. Also, we found that this code coverage analysis is not going to replace any traditional test development or other approaches like fuzzy testing or any other one. The contrary, it's going to complement those. Good news is that we are not alone doing this. SwiftShader driver is also doing it for some months. Even some proprietary drivers are doing it internally. However, if more drivers do the same, they submit issues to CTS issue tracker, or they provide code with the missing coverage for CTS, I mean, it could be great. At the end, all the drivers will benefit from it. I hope we can see more on this in the future, to be honest. This is all. Do you have any question?
I don't see any questions on IRC right now on any of the channels. Yep, so I guess that's it.
Okay, thank you very much.
Thank you for your talk.